So we've got another Game Boy Advanced here. This one's got no audio. It's been worked on by our guys, so it's had things like the ground check on the headphone jack, a new speaker, volume wheel checking, all the basic regular checks our guys would do. And I thought at that point it's probably worth a good YouTube video to find out what the problem here is. So I don't think I've done a video yet covering the GBA audio, from CPU all the way to output. So I'll either do that next, or if this video naturally leads down the route of checking every single part, this will turn into, how the GBA audio system works. But I'm just going to diagnose this, find out what the problem is, and show you my thought train on how I go from no audio to guaranteeing we'll find where the issue is and fix it. So let's just jump in and see how quick we can fix this one. So we've got the console here. I've just chucked a screen in because there's no audio, and let's just make sure the console works. So if we just power it up from the bench, let's first establish we actually have a working console. Yeah, so you can see there we have, well, I didn't load the game that time, that's probably just bad cartridge connector. Let's just try again. There you go, so it's loading the game as well. So if we leave this game running and this in, we can probe around. So we should be hearing audio, and on the volume wheel, obviously we can't. I've pre-checked this speaker on, one, it's a brand new speaker, and two, I just chucked it on a working console. So this is a definite working speaker. So really, we want to start with how do we diagnose this area of the board. So if we just jump over to the schematic, you can get this on RetroSix.wiki under GBA schematics. And this area now we're looking at, here at the edge is the CPU. So this is, what you want to do is go back to where the sound originally comes from, start at the, the first point. So sound comes out of the CPU first in this L and R, and it goes over to R30 and R31 here. That then makes its way into the amp, into right in and left in. It also carries on over here and goes through 3 capacitors and 2 resistors per channel for a dual low-pass filter. So these will feed back the signal into the chip and do a low-pass filter. And then there's some other stuff as well, but basically the starting point is going to be either directly on the CPU, which is normally not broken. So we'll go on to R30 and R31 first, and let's have a look at that signal now. So R30 and R31, as you might spot them, are here. So if I just get my oscilloscope and just pull that up and grip on ground with the oscilloscope leads. And now this side, the right side, goes to the CPU. And this left side, as you can see, comes around, down, and into pins 7 and 8 of the amp. So this is the first point here where we should see audio. And you can see there's the audio, and it's basically a pulse width modulated signal. So if we pulled it up fully, can you see how it's bouncing around? So the width of, the starting point of every high, for example, every 2 highs is the same. That doesn't change. But the width at which, how long it stays high changes. So if you notice, this is moving here, but the width between these 2 points is the same. So it's just a pulse width modulated sine. A pulse width modulated audio signal. So that's one channel, that's the other, so they're both working. Now the other side, once it's gone into the amp, if we take a look on here, is a lower signal. So whether that's what you expect or not, you could compare to a working chip. And I do know that's what you expect, because inside this chip, inside the Game Boy amp, it has more resistor networks and capacitors, and they change the line and pull it low to give you this signal. So that's an expected normal signal. So we know the amp is getting the signal. Well, we say that. Let's probe the actual amp pins to make sure they make it all the way down. So pin 7 and 8, make it to there. So that's pin 8, that's pin 7. You can see the circles on most chips indicate pin 1. There's also an arrow here. So that means pin 1 is here, 2, 3, 4, 5, 6, and you'll get to the end here, 9. And there's this redundant pin here and here. So they probably originally had an amp that was going to have extra pins and didn't. So you've got 9 pins going down here. Number 10 starts here and counts all the way back up to 18. So we've checked that we have audio into the amp. So what's the next step? Let's just take a look at the schematic again. So audio in, the next thing I'd probably check is volume wheel, because that's typically off. So volume wheel's pulled high to the battery voltage, through a resistor, through the volume wheel here, which is just a voltage divider, and through another resistor that keeps it high. So all the vol does is change voltage. So it's effectively a reference pin between the battery voltage and ground. So if we just double check what pin it was, volume is pin 10. So pin 10 is this bottom one here. So if I probe on pin 10 here, and again, try to go to the top of the chip so you know exactly what the chip is receiving at the top end. And if I move the volume wheel, you can see we do have an alteration. The voltage doesn't look right though. But see when I move the wheel up and down, I'm changing the voltage. So it's going up and down. So if I just turn off triggers so it's instant, you'll see a much smoother, live movement. So up, down. So you can see that's all the volume wheel does. When you put ground to the vol pin, there's no audio. When you scroll up higher, you get audio. Now I'm pretty sure this should be from ground to around 2 or 3 volts. So this is too low. So it could be a volume wheel issue, but let's not go digging too deep until we probe further, kind of get a full analysis of the chip to make sure you're not overlooking anything obvious. So volume wheel is working, which means the potentiometer is working because it's moving up and down. Maybe this resistor or this resistor, the top and bottom that keep it at a reference voltage, are damaged or off, so they're suspect at the minute. VREF just pulled to ground through a capacitor, so that'll be ground, but we'll check it anyway. Pin 9. So pin 9 should be ground. Yep. And then I'd probably check the rest of the power line. In fact, I don't think we checked any power lines. Pin 12 should be 5 volts, and pin 14 and 16 should be VCC, which is the battery. That's basically connected straight to the battery. So let's check pin 12 for VDD5 and then pin 14 and 16. So pin 12 would be, if we just zoom in nice and close, you got pin 10 there, pin 11, pin 12. And you can see that's right at the 5 volt lines, that's fine. And then it was 14 and 16, so 10, 11, 12, 13, so 14. And that doesn't look like battery voltage. So there's the issue. Well, potentially one of issues, but that's a big issue because the chip isn't receiving power. So that should be your battery voltage. So that's what it's giving us, just about 0.8 volts. And if I touch my scope on the battery terminal, there we go. So I've currently got the bench providing 3 volts. So we should be getting 3 volts coming into this pin here, pin 14, or rather this pin here, pin 14 and 16 here. And you can see we're getting 0.8 volts. So it's either a broken trace, which to be honest, it's a direct connection to the battery, so it's got to be a broken trace. So I'd stop at this point. Let's just disconnect all the wires so we've got an easy view of the board. And the quick fix for this, if you didn't want to bother, and I do it often if the pins are close, is I'd just send a wire straight from this pin to the battery over here. But let's just, instead of doing that, have a look around. So we could use this board and try and look here and go, oh, where's the wire going? You're going to try and look at pin 14, which is sort of, let's turn that off as well a minute. You got sort of pin 10, 11, 12, 13, 14, but if you see the light of the microscope and the focus, it's hard to try and trace where these vias are going, then turning your board over and losing where you were. So what I've started doing on all boards, and we've got one for the GBA luckily, is I've got high resolution scans that I've scanned in. These are available again on RetroSix.wiki, and this will make this process a million times easier to at least know where things are going. So if you just downloaded the images, and if you've got Photoshop or GIMP or any platform, if you paste the images one on top of the other in layers, then if you hide and show, you'll find that it gives you an exact overlay. If you're working on this side of the board, you want to primarily keep this side the correct way. If you're working on the other side of the board, you'll notice it's flipped, it's mirrored. So I've flipped it purposely so when you hide and show layers, you can see, say we wanted to see where this via went here, we can just hide the layer and instantly see that it's this via. So we mirror them in order to do that. So the image is already pre-mirrored, But say you wanted to work on this side of the board primarily, you could just like say in Photoshop, image rotation, flip canvas horizontally, and then this side of the board becomes the right way and the other side becomes mirrored. So it depends which preference you want to work from in terms of ease of, looking at what you're doing. So in our case, we are working on tracing. So let's have a look and try and memorize where it goes. So here's pin 14, and if we zoom in, you can see pin 14 comes down, goes to these two caps here, which will be C51 and C50 coming off pins 16 and 14. They are just decoupling capacitors. And then it goes into obviously pin 16. So pin 14 and 16 loop here, and the power goes through these two vias. So if we show the other layer, these two vias now, one goes over to here, which goes to this resistor, which goes into the volume wheel. So that's that pull-up resistor to the top pin of the volume wheel. That's the one we suspected might be wrong, but the fact that we don't have the right voltage, I'm guessing it's just this voltage. So we don't want to go that way to the via going the other side of the board. We want to follow this trace around here. You can see it comes around, up. And you see how easy this is with a scan that's clean and easy and, a fresh board to see. Now you've got a via here. Be careful, you can see this is actually connected to this trace. So we want to follow that potentially. But it also carries on up here. So it goes all the way up here, through this via, into this resistor, and then it'll go the other side to the diode. We could trace where that is, but that's not where we're trying to go. We're trying to go over to here by the battery spring. So ignoring what that is at the minute, we know going up there is not where we want to go. The only other place the power seemed to go was through this via. So let's follow that one. So it goes up, past the cartridge pins, all the way across the top of the letters, to this via, across to this via, across to this via, wiggle through to two vias here, which go up through the current limiting resistor and into the regulator. So we don't want to go that way. We're not on regulator side, we're directly to battery. So ignore those two vias, carry on following the trace through, gets to a thin piece here. So you can see that's quite a thin piece of trace there, so that might be worth looking at. It goes down here to two more vias. Then these two vias come down diagonal and down here. They come through, and then all this pad, because you can see how basically, see how it's a dark colour. So here's the outline. When it's a lighter colour there, that's like there's no copper, so that's a break. That's how I'm kind of following the traces. You can see, either side where it's light, it isn't connected. So this comes down here, gets wide here, fills all this area, connects to the main CP1 capacitor. Those two vias go into the transformer the other side, so we don't care about that. That's again part of the regulation. And then from there, they go, and it gets a bit hard to see here because you've got a white here, which is the silk screen, and then you've got the solder resist green here, but you can see the edge actually here. So it comes off this via, it goes down and into the C pin of the power switch, and then over to, or rather the power then from the battery spring here comes through fuse 1 and into pin 2. So when the switch is working, the power will come into pin 2, through here through a metal spring in the power switch and out to C. So that's the entire power path. So the first thing I'd do for quickness is to probe for voltage. So I'd probe at the battery spring that we did to see it was 3 volts. Then I'd probe, say here, on the big CP1 to see if it's still 3 volts. So we know that the trace isn't broken and the power switch works. Next, I'd probably go through these two vias. Maybe because this thin trace might be broken, I would... where would I probe next? I'd possibly probe... Oh, this is going under a capacitor here. So this is underneath CP3. So we can't easily probe that. But what I will probe is this pin here. So we're a good distance away. So if we probe, if we look for where the clip comes into the cartridge connector and the plus arrow here, it's this via here. If we haven't got voltage here, we know the break is somewhere in this trace area. If it does get voltage here, it's a straight line all the way across. And then not much to probe around here. Comes down through. So if we just memorize where it was again, comes through these 2 dots, all the way around, and the next point out really is above C45, and then it's just a big long trace over. So we should have enough knowledge there to start hopefully probing the actual board. So let's just bring the board back in, and I guess we can power the board up. Probably quickest and simplest. You could do continuity and stuff, but I think just bringing up the scope and doing direct voltage test is probably fine. And you can use, the beauty of the oscilloscope is you can use it as a multimeter as well. You don't need to just use it as a scope. You can just grip your oscilloscope on and probe around and just look at the traces here for voltage. So if we turn on, and I will probe here first, which we have 3 volts. So if you remember where that line is, that's your 3 volts. Bypass the switch, go straight to the cap. We've still got 3 volts, so we know that's good. The next point was, I think we said, up by this plus arrow, and it's this here. So if you remember on the scan, it's this via here, this one by the plus, and that's still good. Once you break through, you'll have to push a bit firm because obviously you've got solder resist in the way. But if I push on it like that, you can see we still have the 3 volts. So we're good there, which means it goes all the way through underneath this cartridge connector. Yeah, so there's C45, so it comes out above this dot here. So if we're not getting connection, so the break is probably under, of all places, under the cartridge connector likely. So let's just scrape away a bit of this resist. And I might as well scrape away enough to solder to, because if this is broken here, I'm not going to take the cartridge connector off, I'm just going to go under here. So that's that off. Now let's probe on that pin. Ah, no, I just wasn't breaking. Well, I say that, we've got it to this point. It might be broken on the via. The via itself might be broken. So to test that, if we jump back to the file, we're now suspecting maybe that this via is broken because we're getting power now here, but possibly this via, once it's gone under, is broken to this trace. So if we flipped the board around, or let's follow it around to where it next goes. So the next point really, yeah, is it goes straight to the chip. It goes to this pin here. The power's here. So I'm pretty sure this via is the problem. So what we'll probably do is run a wire. We can test with I'll test with a multimeter. That's probably the quickest. Now scrape some resist off here, or let's just scrape some resist off on the other side, flip around, and check if it's lost the power, because that's looking like what it is. So let me just disconnect the power connectors for a minute, flip around, and oh, and look at that. We suspected what it was, and there's acid corrosion. So see that dot there, and all that black, that's acid corrosion. So that is the problem. So we just scrape away, and it's got, of all the holes, it's got acid in that hole. So that via is blown out, and no good. So you can see it's just all black when we're scraping. So it was good to see that on the scope we predicted that it was about to be there, and then it spotted that the trace was bad. So for this, I'm just going to run a mini trace around. So we could have been lazy and just done a wire all the way back to the battery. But when you want to take your time and do it right, and make a cleaner job in some instances, then you just spend that little extra time finding where the trace is broken and do a shorter repair. So with that now, probably need some flux here, but there we go. So we've got that pre-tinned. Let's flip over and let's pre-tin this area. There we go. And I'll just use some Kynar wire. I'll roughly measure it, so I want from there. Put a little bit of flux on here now. for now. Pop the wire close to the scrape off, try and get it in line ideally. So just try and pre-bend your wire as much as you can. This capacitor's getting in my way. And line it up sort of with the line of the solder with flux on and solder already on your iron. That's a nice easy solder, so that's now on. And then just gently bend it around the other side. And we'll do the same here. A little bit of flux. Solder on the tip of the iron. It lines up with the trace like that. And just warm up. And that's a connection. This is why I'd normally want to use enamel wire. I just don't have any on me at the minute. Because you'll start melting the insulation on plastic insulation. Enameled wire is coated with, as the name suggests, enamel, and it's a lot more heat resistant. So I'll grab some enamel wire as we progress so you can see how I'd normally do these repairs to make them nicer. But at least let's do one more step on here and show you how to do a nice repair. Let's clean it with IPA. We'll first check that this has fixed it as well. There's no point cleaning up a work if that isn't the issue. Just do your cleanup last. So I'm just going to get the solder flux off there at least. So now let's test this works. If it works, we'll clean up that connection. So battery, volume wheel all the way up. Connect the battery springs. Connect it on there. And there you go, you can already hear the audio. So this isn't amped, this is the original stock audio, but I'm sure if I hold it up a little bit you can hear that. Oh, the power connector didn't drop off. So if I turn that on. So that's now fixed. If you want out of curiosity, just bring up the scope. And I'll show you now what it should look like on the lines. So if we were to now probe what we originally had down here, which was the vol pin, which I think is pin, like, go off the third here, which goes into pin 10, is it there? And if I turn it, oh, get that on. Stay on pin 10 there. And if I turn the volume wheel now, and you can see the volume wheel going up and down much more dramatically. And if we look at the voltage level, it's at the battery voltage input. So that's how your volume wheel should work. It should go from battery voltage. As you go down on volume, it should go closer to ground, but not quite to ground. So that's now working. And obviously, pin 14 and 16 should now be 3 volts, which they are. So let's now quickly just clean this up. So what you'd want to do here, if you want to make a really neat job and make it look a bit more like stock, you've got exposed copper, you've got exposed conductive wire here, which doesn't look the best. So what you can do is get conformal coating, as I call it. Most are okay. UV curing solder mask, this is called. So the green stuff is solder mask. It's sometimes called conformal coating, but basically this is solder mask. So this green stuff we've scraped off, we can put back on. So I'd apply it with a cotton wool bud, because you don't need much at all. And then I would just get the tub. You should have a plunger. I've just lost mine at the minute. So I'm just going to push in with that. Get a little bit on there. You don't need much at all. Move that out the way a minute. And then on here, I know this is white, so if you want to make it really nice, you'd get some white solder mask. So it's the same, but I'm just showing you the principle here. So if we loop that over, and basically now, so long as it's covering, that will act as electrical insulation, just like the solder mask does. So you can cover it over the wire as well if you wanted. So that's going to be making this electrically non-conductive when you touch it. To cure it, you just need to grab a UV light. So I've got one here, just an Amazon jobby. And it's a normal light if you press it, and if you hold it, it turns to UV. So I'll just put the UV light on, and it normally takes, depending on how good your UV light is, this is quite a strong UV light. It can take 5 seconds, can take 30 seconds. You can also use your hot air gun if you've got it as well to warm up at the same time. That assists in the drying process. So the hot air evaporates the moisture and the UV sets the ink. So if we look down there now, once it's set, it will look sort of dry and crusty almost. So it's still got a little bit of a sheen on here. So if I turn on my hot air at the same time, and it just takes a few seconds with hot air, and just literally put a bit of hot air near it, and you get a really fast dry then. You don't have to wait around much. And you can see there now, see the texture change to like a dry. You can tell it's basically now got a matte finish. So that's now cured. And you can touch it, it'll be dry. And it won't be conductive. So it's just a better finish. It's also a bit of mechanical stability. So the wire is now mechanically held in place. So you can bend this wire and it doesn't move underneath it. So if that was white resist there, you'd see that would look neater. The other side, we can do it here. And this isn't necessary. This is just extra steps you can take depending on what you're repairing, or what, say you're repairing a £1,000 console. You want to use enamel wire and correctly coloured solder mask, and you can make a really neat repair job. And it's just that extra level, especially if a customer's paying for it. Say this is somebody's pride and joy Game Boy that they've had since a kid. These are the steps I'd take. If it's somebody that's not really that bothered and they just want it repaired and they're having upgrades anyway, they might not be that fussy and they might not have paid that much for the repair side of it. So obviously you judge your work on how much time you want to invest in each step, but when you're doing a trace repair, this only takes a few minutes extra, and it just adds that extra level. If somebody opens up this and sees inside that you've got conformal coating over and it looks nice and solid and done right, it gives you that extra level of cred as well. So I'd recommend it, and we'll do it going forward when we do videos, just so people following this follow suit. Basically they'll see that we do it and they'll want to do the same. So that's the repair there, and that's now your kind of official repair. If that was enamel wire and this was white, that'd be as neat as a repair as I'd expect anybody to do. So hopefully that was useful. You can see how we've diagnosed and repaired the audio. I will do a separate video on how the whole audio system works, because we really only got from the CPU pins here to the chip, and we didn't look at the low pass filter, we didn't look at the headphone socket. I briefed over this, so I'll do a separate video on how exactly all the audio system works. But hopefully these little random repair videos do assist you, and you can learn from them. If you got any requests, let me know in the comments, and I'll see you in the next one.